All right, let's take a look at problem 2. So mixture contains N-peptane and hexane and N-heptane at equal mole fractions. The temperature is 55 degrees C. And so equal mole fractions. So that means Z1 is equal to Z2 is equal to Z3. And that's equal to a third. Okay. And before I even look at this, right, I've got a mixture of pentane, hexane, and heptane. So linear alkanes, C5, C6, C7. So assuming an ideal solution should be reasonable, I just have a mixture of alkanes, so chemically similar compounds. So all of those alkyl interactions should be exactly the same. Okay, the temperature is 55 degrees C. Right, so I'm thinking of PXY, so temperature is fixed. And I look at the bottom at 55 degrees C. We're given the vapor pressure of pentane, hexane, and heptane. So 1.9 down to 0.231 bars. So we're going to be operating at low pressures. So assuming a vapor phase is an ideal gas should also be reasonable. All right, so Raoult's law should be reasonable to model our system here. We have chemically similar compounds, so assuming an ideal solution should be reasonable, and at low pressure so that we can assume our vapor phase is an ideal gas. Okay, so we have this ternary mixture at 55 degrees C, and in A we're asked to calculate the bubble and dew pressure at 55 degrees C, and then in B and C we're asked to identify a phase at a given pressure at that same temperature of 55 degrees C. And for two phase, we need to identify the composition and then the amount of my two phases. And then D is going to be similar. Okay. So the first thing I'm going to do is I'm going to draw a picture. All right. So just to make sure I understand what I have going on. And so even though this is a ternary system, I'm going to sketch a phase diagram for binary system. Right. It's going to be for binary system, but conceptually, right, my description of my system is going to be exactly the same, or how I'll use it to walk through my solution is going to be exactly the same, right? I'm just going to use it as a guide in terms of solving this problem. And so we're told that we're at 55 degrees C, and then in B and C, right? In A, I'm going to calculate bubble and dew pressure. In B and C, I'm asking for the state of my system at that same temperature, but at a different pressure. Right, so I'm thinking about a PXY, right? A PXY in which the temperature is fixed. So if I sketch a PXY, okay, so I'm going to sketch a PXY for a binary system. Okay, so if I sketch a PXY for binary system, okay, this is P1 sat. P1 sat's greater than P2 sat. My apologies, on this computer, my tablet's a little sensitive. So I'm going to connect P1 sat and P2 sat via straight line. So let me just move P1 sat so it's on a straight line. And then my dew line, right, is going to be some curve. Okay. So it's a PXY, temperature is fixed. High pressures favor liquid, low pressures favor vapor, and in between, right, well then I'm two phase. Okay. All right, so what I'm going to try and do in this problem, okay, is I'm going to have some system of known composition. So here I'm just drawing in some vertical line corresponding to a composition. Here I'm calling it Z1. So I have some mixture of some given composition. And so if I were to say start up here in my liquid phase, as I decrease the pressure, okay, where I hit my bubble line, that corresponds to the bubble point of my mixture. What's unique about my bubble point is that my bubble point, right, I read liquids for my bubble line, is that my bubble point, x1 is equal to z1. If I were to continue to decrease the pressure, okay, where I hit my dew line, that corresponds to my dew point. And what's unique about my dew point is that my dew point, y1 is equal to z1. Okay, so what I'm going to try and do here is for a mixture of a given composition, we're asked to calculate my bubble point and dew point pressure for that mixture. Right, what's going to be key is that my bubble point, x is equal to z, and at my dew point, y is equal to z. I'm going to calculate my bubble point and my dew point, right? And the idea is going to be is these are going to serve as two reference points so that if my pressure is greater than my bubble point pressure, well then I'm up here, right? That means I have a liquid. If my pressure is less than my dew pressure, then that means I have a vapor. And if my pressure is between my bubble point pressure and my dew pressure, well then I'm in my two-phase region. I have a two-phase mixture. Okay. Cool. Now let's talk about bubble P and dew P calculations. Okay. So the key of performing my bubble P calculation is that at my bubble point, okay, I have a system at two-phase coexistence. Okay, so I have a system at two-phase coexistence where my liquid composition is equal to Z, my mixture composition. So my bubble P calculation, okay, I have a system at two-phase coexistence, so I'm going to write down my three isophygasity equations for my ternary system. So I'm going to have Y1P is equal to X1 P1 sat. So again, I'm assuming Raoult's law is applicable. Vapor phase is an ideal gas. Pure component at saturation at T is an ideal gas. So vapor phase is can be treated as an ideal gas. Pointing correction is negligible, and liquid phase is ideal. So Y2P is going to be equal to X2 times P2 sat. And Y3P is equal to X3 times P3 sat. Now the key of a bubble P calculation is I know P1 sat, P2 sat, and P3 sat. Right? In fact, by specifying T, right, P1 sat, P2 sat, and P3 sat are only functions of T. So by specifying T, that's the same as specifying P1 sat, P2 sat, and P3 sat. Okay, so P1 sat, P2 sat, and P3 sat, right, I know those. Okay, X1, X2, X3, right, I know those because at my bubble point, X1 is equal to Z1, and I know Z1, Z2, and Z3, right, they're all just a third. Okay, so I'm going to know my X's. Then on the left-hand side, I don't know Y, and I don't know P, right? P is what I want to solve for. Okay, I don't know Y. And so in a bubble P calculation, the idea is if I sum these two equations together, on the left-hand side, okay, I end up with Y1P plus Y2P plus Y3P. Okay, well that's P, that's my pressure, right? It's the same, I can factor it out. I have Y1 plus Y2 plus Y3. Okay, Y1 plus Y2 plus Y3, well that sums to 1. Okay, so when I add this up on the left hand side, I'm just left with P, and on the right hand side I have X1 times P1 sat plus X2 times P2 sat plus X3 times P3 sat. Okay, so the idea is I sum them together, and what that does for me is on the left hand side it allows me to kill Y. All right, and I kill Y because I don't know Y, and P is the quantity I want to solve for. Okay, so by adding them together, I can kill Y, and on the left-hand side, I'm just left with that quantity I'm trying to solve for. Now, the key to make this complete for bubble P calculation is that my bubble point, X1 is equal to Z1, right? So my X's are equal to Z, okay? And then when X is equal to Z, well, that pressure corresponds to my bubble point pressure. So I'm going to write this as P bubs is equal to Z1 times P1 sat plus Z2 times P2 sat plus Z3 times P3 sat. Okay, I'm just going to box this in for now, and then we will calculate it in a second because I will then label my phase diagram so we can identify phases. All right, so that's my bubble point pressure. Okay, and I'm going to leave a little space so I can write in. So let me just write in here, right, P bubs for when I calculate it. Now I want to do a do P calculation. Okay, do P or P do. So do P calculation. Okay, now the idea is that my dew point, right, I've got the same situation. I've got a system at two-phase coexistence. Just now my Y1s are equal to my Z1s, which I know. Right, so I'm not going to kill Y in this case. So I'm going to write down my isophygasity equations. So Y1 times P is equal to X1 times P1 sat. Y2P is equal to X2 times P2 sat. Y3P is equal to X3 times P3 sat. Okay. So now, in this case, I'm going to know my Y's, right? Because my Y's are just equal to my Z's, which I know. And I want to calculate P. On the right-hand side now, I don't know my X's, but I know P1 sat, P2 sat, and P3 sat because temperature is fixed. So I'm going to do a similar trick where I'm going to add my three equations together, and I'm going to do it to kill X in this case. But in order to kill X, right, by X1 plus X2 plus X3 is equal to 1, what I'm going to do is I'm going to divide through by the saturation pressure. So this becomes Y1P divided by P1 sat is equal to X1. Y2P divided by P2 sat is equal to X2. And Y3P divided by divided by P3 sat is equal to x3. Because now when I add them together, okay, on the right-hand side I just have x1 plus x2 plus x3, right? That's just 1. On the left-hand side, when I add these together, right, this is the same p, right? So if I factor out the p, I have p times y1 over p1 sat plus y2 over p2 sat plus y3 divided by p3 sat is equal to 1. Solving for p, I end up with p is equal to, so the inverse of this, so I'm going to write as y1 over p1 sat plus y2 divided by p2 sat plus y3 divided by p3 sat raised to the negative 1. Okay, or to make it complete, so at my dew point, y1 is equal, or my y's are equal to my z's. So I end up with p dew is equal to z1 divided by p1 sat plus z2 divided by p2 sat plus y3 divided by p3 sat. Okay. Here, now y3 is z3. Okay, I'm going to box that in. Okay. Now before I go over to MATLAB to compute it, right, so I can get my reference point for my graph, okay, what I want to remind you of is when I perform my bubble P calculation, right, so we had to do this for problem 1 as well. We had to do P bubs and P dew just for a binary system. So remember, my bubble point pressure is just the molar average, right, of my pure component saturation pressures. Okay, and so this is where when we sketch a PXY for an ideal system, so a system which we can assume the liquid phase is ideal. So if we have a system that obeys Raoult's law, my bubble line is just that of a straight line, right, from P2 sat to P1 sat. Okay, because, right, my bubble line is described by exactly this equation, right? So my bubble line is a straight line. When we have a system that obeys Raoult's law, right, my bubble point pressure is just the molar average of my pure component saturation pressures. Okay, we'll look at deviations from linearity in chapter 12. All right, so let's go ahead. I'm going to jump over to MATLAB and we'll compute these values. That way I can get them on my graph. So let me get a new script. I'll save this as problem 2. I'm pretty sure. Okay, so in problem 2, we have z1 is equal to third. Okay, z2, so it's equimolar. And z3, I guess I just could have used like a z variable, but I'm going to put it all out for completeness. So z1 is equal to z2 is equal to z3 is equal to third. P1 sat. Now let's see, all the pressures are in bars, so my answer is going to be in bars. It's 1.903. P2 sat. P2 sat is 0.644. And P3 sat is equal to 0.231. Cool. So then to calculate P bubs, so P bubs was just Z1 times P1 sat plus Z2 times P2 sat plus Z3 times P3 sat. And P dew, it's equal to, well, I don't want to use brackets. Brackets aren't allowed. Okay, but it's going to be Z1 divided by P1 sat plus Z2 divided by P2 sat plus Z3 divided by P3 sat. And it's the inverse of that, so that raised to the power of negative 1. So if I run it, I get a P bubs of 0.9260 and a P dew of 0.4682. So this, so x1, or where x1 equals z1 at my bubble point, okay, I get this as a pressure of 0.96, 0.9260, 0.9260 bar, and down here P do is 0.4682, 0.46 bar. Okay, cool. So now I've got my bubble point and my dew point. And so again, the key is if my pressure is greater than my bubble point pressure, I'm up here in my liquid. If I'm below my bubble or dew point pressure, I'm down here in my vapor. And if I'm in between, I have a two-phase mixture. Okay. So in terms of B now, what is the phase of the system at 1.7 bar and 55 degrees C? The key is my pressure is greater than P dew. All right, so I'm going to be a liquid. Okay, so B, okay, now I know my system's going to be a liquid at 1.7 bars. Okay, cool. But what about at 0.5 bars? Well, 0.5 bars greater than my dew pressure, which is 0.4682, and less than my bubble point pressure, 0.9260. So now in B, or C, now I know I'm going to be two-phase. Okay, so I'm going to be in my two-phase region. And the question asks, what is the composition and the amounts of each phase? Okay, so let's calculate this. Okay, oh, I got to write this down here. So we calculate P bubs and P dew. Okay, and what I'm going to do is, I'm just going to go off on an aside, right? Because I just want to highlight what's different or special about ternary systems. Okay, is if I have a binary system. So let's look at the exact same problem, but if I have a binary system. Okay, so I have a binary system, and in the problem, all right, we're specifying temperature and pressure. Okay, now remember when I specify temperature, okay, that's the same as specifying P1 sat, right, and P2 sat. It's the same as specifying my pure component saturation pressures, because P1 sat and P2 sat, my pure component saturation pressures are only a function of T. All right, so if I have a binary system, well, then I'm going to write down my phase equilibrium expressions, my isotopic acid equations. And again, here we're assuming my system could be modeled using Raoult's law. So that's going to take the form of Y1P is equal to X1 times P1 sat, okay, and Y2P is equal to X2 times P2 sat. Okay. Then to make it complete in terms of solving, okay, I know that I have my constraints that Y1 plus Y2 are going to be equal to 1, and X1 plus X2 is equal to 1. Okay, so for binary system, okay, if I specify temperature and pressure, so temperature, that means P1 sat and P2 sat are fixed. If I specify pressure, right, then I know P. Okay, so in terms of unknowns, right, I have four unknowns: Y1, Y2, X1, and X2. I have four unknowns, but I have 1, 2, 3, 4 equations. Okay, so for binary system, when I specify temperature and pressure, similar to this problem, I have a system of four equations with four unknowns, which I can solve for Y1, Y2, X1, and X2. Okay, so for a binary system, I can just go ahead and I could solve my phase equilibrium expressions, calculate the composition of my two phases, and then if I wanted to know amounts, I could use a mass balance, which we'll talk about here in a second. Okay, but all right, so that's an aside, right? So let me add a new page. Okay, so I put a new page so that this comment's there. Okay, so let's talk about a ternary system, right? Because ternary systems are going to be a little special. Okay, so when I have a ternary system, though, okay, so when I have more than two components, in this case 3, okay, we're again specifying temperature and P, and by specifying temperature, okay, that means that I'm fixing P1 sat, P2 sat, and P3 sat. Okay, so again, I start by writing down my isotopic acid equations. Okay, so I'm going to have Y1P is equal to X1 P1 sat, Y2P is equal to X2 times P2 sat, Y3P is equal to X3 times P3 sat. Okay. Now I have my constraint equations again, that Y1 plus Y2 plus Y3 are equal to 1, and X1 plus X2 plus X3 are also equal to 1. Okay, so pressure is specified. Okay, specifying temperature, that means P1 sat, P2 sat, and P3 sat are also specified. So if I look at my system of equations, right, my phase equilibrium expressions, okay, in terms of unknowns, I have y1, y2, y3, x1, x2, and x3. So I have 6 unknowns, but I only have 1, 2, 3, 4, 5 equations. So I have a system of 5 equations with 6 unknowns. Right? I can't solve that to obtain a unique set of y1, y2, y3, x1, x2, and x3. Okay, so I end up with 6 unknowns and just 5 equations. Right? I can't solve it. So I need more equations. So how I'm going to get those is I'm going to set up my mass balance. And what's going to be special is for a ternary system, you need to simultaneously solve your phase equilibrium relations with your mass balance expressions. Where for binary system, you could solve your phase equilibrium expression independent of your mass balance. Then if you wanted to know amounts, you could then solve your phase equilibrium expressions and then subsequently solve your mass balance expression. Okay? But let's go to a ternary system, which is what we have. So how I'm going to get those extra equations, so I'm going to try and draw it down here towards the bottom of the page, is I'm going to draw my schematic for my simple flash drum. Okay, where my feed, well, that's going to correspond to my system. I'm going to have some amount of, so my system's going to contain some moles, right, of my mixture, right, F. It's going to be of composition Z1, Z2, and Z3. Okay, and those are all equal to a third. Okay, and so I'm going to have some equilibrium unit at a given temperature and pressure. Coming off the top, I'm going to have some vapor. So V is the amount vapor of composition Y1, Y2, and Y3. And coming out the bottom, I'm going to have a liquid of composition X1, X2, and X3. Okay. Now when I write this out, F, V, and L, those are all extensive quantities. That's the number of moles in my system, the number of moles, so total number of moles, say, in my system. Then this is the number of moles of my vapor and the number of moles of my liquid. Okay, so if I want to solve for, V and L, right, the amount vapor, amount liquid, then I would need to assume a basis, right? And so how I typically would solve it is I would assume a basis of F is equal to 1. Okay, the other way we can do it, and I'll show when we write down our mass balances, is we can perform all of our calculations on a relative balance. But if I assume F is 1, I calculate V, well, it's V relative to an F of 1, it's equivalent to V over F. Okay, but I'll show you what I mean here. Okay, all right, so if I write down my schematic here, for my ternary system, I could write down 3 mass balances. Okay, so I'm going to write down 3 component mass balances. Okay, and so what I'm going to have is I will have Z1 times F is equal to Y1 times V plus X1 times L. Z2 times F is equal to Y2 times V plus X2 times L, where Z3 times F is equal to Y3V plus X3L. Okay, so now I've got my phase equilibrium expression with my constraints that my mole fractions have to sum to 1, and now I have my 3 component mass balances. And so if I look at this, right, if I were to assume a basis of F is equal to 1, because I need to give a basis. So if I specify F is 1, now what I have, right, is before we had 6 unknowns and 5 equations. So when I add my 3 mass balances, I'm going to add, so my Z's are known, right? And again, if I assume F is known, if I take that to be my basis, I had 3 equations with 2 unknowns, right? My 2 additional unknowns are V and L. So now what I end up with is I end up with a system of 8 equations with 8 unknowns, right? 8 equations, and then my 8 unknowns, Y1, Y2, Y3, X1, X2, X3, V, and L. Okay, so I end up with a system of 8 equations, 8 unknowns. Now the other way I could do it is often, right, if I were doing this, I would just assume a basis of F is equal to 1, calculate V and L, and that would just be, relative to a basis in F of 1, right? So calculating V then relative to an F of 1 would be the same as V over F, right? So it'd give me the fraction vapor, right, fraction liquid. The other way you could do it, right, is I could divide through by F. Okay. And if I divide through by F, okay, then this is going to become, I'm going to end up with V over F and L over F. And I could just take V over F and L over F to be, right, those distinct quantities or variables that I want to solve for. Okay, so this becomes V over F, V over F, V over F, L over F, L over F, L over F. Right. So in this, I could take V over F to be, right, a variable, right, fraction vapor, L over F to be a variable, fraction liquid, and I could just directly solve for those ratios. Right? But the key is, if I have a ternary system, my phase equilibrium expression and my mass balances need to be solved simultaneously. When I have a binary system, I could solve my phase equilibrium expression independent of my mass balance. And so if I wanted to know amounts, I could. Lost for words, I could first solve my phase equilibrium expressions on their own, and then I could solve subsequently my mass balances. Okay. But all right, so if you want to stop this video now, you can. Otherwise, I'll attempt to set this up in MATLAB. Okay. All right, so what I'm going to do is I'm going to save a copy of this, and I'm going to call this problem 2 system. Okay, so this is going to be when I'm solving my system of equations. Okay, I'm going to set this up as a function for problem 2 system. So it's going to be a function with no inputs. And then I'm going to delete this. And then, all right, so if I want to set this up as a system of equations, I'm going to use fsolve. And so I'm going to need a helper function in which I program all these up. Okay, and then I'll try my very best to put it all together. Okay, so I'm going to have function res is equal to airfunc. Okay, and in terms of unknowns, okay, it's going to have that unknown that I'm going to try and solve for, and then I'm also going to pass to it z1. And actually, what I should probably do is let me just hard code these. So let's keep it simple. Just have an unknown of x, and then I'm going to paste in. Oh, why didn't that paste right? Paste in. I'm going to paste in what we have. All right. So what I'm going to do is x. That's going to be my variables that I'm trying to solve for. So I'm going to unpack x. So if I unpack, I just want to get this in terms of variable names, which are in line with what I'm going to have in my equations. So I'm going to have y1, y2, y3, x1, x2, x3, v over f, and L over f. So y1, I'll just make the first element of x. And this is just going to make it easier when I set up my equations. y2 is going to be my second element. y3 will be my third element. And then I'll have x1's my fourth. x2 is my fifth variable I'm trying to solve for. It's been a while since I used fsolve, so hopefully I get this right. x3 my sixth. Then v, it's going to, v over f, I'm just going to call v. Let's call it vf. vf will be my seventh. And then fraction liquid, lf will be my eighth. All right, so then what I need to do, I call this res, I call it y, right? I need to set up my series of my air functions. So now my system of equations. Okay. So when I set this up as air functions, I just need to make it so all of these expressions evaluate to 1 when I find my solution. So instead of y1p is equal to x1 times p1 sat, it's going to be y1p minus x1 times p1 sat, because that'll be equal to 0 at my solution. Okay. So my first equation, okay, so my first air function, which could assign to y1, it's going to be y1 times, did I put p in here? No. So in this problem, P is equal to 0.5 bars. Okay, so my pressure is equal to 0.5 bars in this case. And again, I should make this more general, where I pass these quantities to my function, but I'm hard coding them here, right, to make it simple. Okay, so y1p minus x1 times p1 sat. Okay, I'm going to copy and paste. Second equation is y2p minus x2 times p2 sat. Third equation, y3, my third equation, y3 times x3 times p3 sat. Now my constraint equations is what I had next. So we had that my vapor mole fractions need to sum to 1, so I'll do 1 minus this, or this minus 1 is equal to 0. Doesn't matter which way I do it. So I'm going to do 1 minus y1 plus y2 plus y3. Same thing for the liquid. So my fifth equation, copy and paste and replace y with x. Bam. Okay. My sixth equation. Now I've got my component mass balances. Okay, again, I'm just going to set this up so it's so I'm going to do this. I do this minus that, or vice versa, right? So that evaluates to 0 when I find my solution. I'm going to z1 minus, okay, in parentheses, y1 times vf plus x2 or x1 times lf. All right, z2. Oh, so seventh equation. So z2, y2, x2. And then my eighth equation, c3, y3, x3. Okay, cool. So if I want to solve, okay, so my solution, I'll use fsolve. Okay, so I've got my air function. Okay. Okay, and then I need to give it my initial guesses. So now the key is when I give my initial guesses, it's x1, x2, x3, or no, y1, y2, y3, x1, x2, x3, and fraction vapor, fraction liquid. Okay. All right, so let's just try and come up with something, right? Oftentimes I use rand, and actually let me do that. So let me do so my x, well actually y guess. So y guess is going to be so rand what's my random number generator? Pretty sure it's rand. Yeah, uniformly distributed random numbers. 1 to 100. So rows, then column. So rows, then column. But I'm unpacking. So I'm going to do 3 comma 1. So that'll generate random numbers between 0 and 1, which is fine. That's what I want. X guess. Let's be rand 3 comma 1. And then I can do the same thing for VF and LF, right? I know VF, well, I could get something a little more intelligent. So actually, so if I'm doing this, and V over F and L over F are going to be between 0 and 1. Okay, this should just be rand 8 comma 1. Okay, so let me start by running this and see what happens. Okay, so it works. So this should be y1, y2, y3, x1, x2, x3, fraction vapor, fraction liquid, right? Does it make sense, right? So in my picture, okay, I'm going to be closer to my dew line, right? So I expect to have more vapor than liquid, okay, since I'm closer to my dew line, right? So I get that I'm almost 89% vapor, right? And I only have a small liquid percentage. So cool, right? So there's my y's, there's my x's, okay? So y1's greater than x1, cool. There's my fraction vapor, there's my fraction liquid, okay? Cool. So if I were to write this out, okay, so let me just write it out for completeness just so you can see it, because then we'll just update this for the next problem. Okay, so y1, y2, y3, x1, x2, x3, then we had v over f and L over f. Okay, so that's the order, right? The order is the same as I have here. Okay, so I would just copy these numbers down here that I next to those variables that I just listed. Okay, cool. Okay, so this is part C. Okay, cool. Now what's going to change? So actually I'll just set it up in here. So what's going to change in D is, so that's C, right? So I specify the pressure and I knew the temperature. Now what's going to happen is in D, we're told that the pressure is going to be adjusted, right? So the difference is now in D, I don't know P, right? So P is going to become a variable that I'm solving for. So the pressure is adjusted so that 75% of the mixture is vapor, while the temperature remains at 55 degrees C. So temperature remains the same as 55, but I don't. I now know V over F, but I don't know P, right? So I'm just going to have to set it up. So if I come here, okay, and so I'm going to make P my last variable just in the interest of simplifying this. So I'm going to make L over F my 7th variable, and then I'm going to make P my 8th variable. Oh, and actually, before I do this, I'm going to make this, I'll do an underscore D to make this D, right? That way I've got system and system D, right? So you have everything. Okay, so I'm going to make variable 7 my L over F, and variable 8 I'm going to make P. Okay, then instead of specifying V, I'm given V over F is 0.75. Okay, cool. So P is my last one. In terms of my initial guesses, okay, I'll just use a random number between 0 and 1 for P. Right, I know P, all right, should be between 1.9 and 0.231. Okay, so, but yeah, we'll just use a random number between 0 and 1 and see what happens, see if it solves. Okay, so if I run this, right, hey, it worked. Okay, so L over F is 0.25, right, and that makes sense since V over F is 0.75, L over F is 0.25, so that checks out. And now my pressure is 0.5479 bars. Right, so my pressure is slightly higher than the last problem. Right, it's 0.5479 bars. Okay, so this would be y1, y2, y3, x1, x2, x3, L over F, and then P. Okay, and so again, y1's greater than x1, right? So that checks, right? Component 1's my most volatile component. Okay, cool. So there you have a solution that works for part D. Then this one was part C. Again, if I have more than 2 components, I need to solve my phase equilibrium expressions and my mass balances simultaneously, so I get compositions and the amount in those phases all in one swoop. If I had a binary system, I could solve my phase equilibrium expression independently from my mass balance, so I could first solve for compositions, and then if I wanted to solve for amounts, well, then I could draw the same picture, right, just for a binary system. Okay, but cool. Hope that helps. I'll have the MATLAB code posted along with my solutions. Yeah, because that's the last one. So let me know if you have any questions. But hopefully that helps.